Hi, this is Jez from About Slingshots YouTube channel. In this video we are going to examine the inner workings of slingshots, or how slingshots actually work. But this will be a long and demanding video, and if you are right now in your analytical mood, then this video is for you. There is no math here. The background math was done by my Slingshot Setup Designer, or SSD, which you can download for free from my Google Drive. The download link is below in the description, and if you like the program, please support its further development by a donation. In order to understand how actually slingshots work, we need to examine a typical slingshot shooting situation. So you draw your pouch to your preferred anchor point, and then you release. And then your ammo and your pouch and your rubber, they travel or they go in a given direction. But before we go on, there is a very special point somewhere halfway between your full draw, actually the anchor point, and the fork tips, and for heavier ammo it is a little bit to the right, and for the lighter ammo it is a little bit to the left. And this is the point where your pouch stops accelerating your ammo. This is the point where ammo becomes the projectile, or where its free flight begins. And then your ammo goes on, hits the wall, falls to the ground, or whatever. And as a curiosity, if you say that you shoot 10 meters range, then 10 meters starts here, and wherever 10 meters are. Of course, this is not practical for any realistic shooting situation, but it is the fact. So, at this critical point, your ammo receives exit velocity and exit energy. And what happens until this point, or what brings your ammo to this specific velocity and to this specific energy, is studied by Internal Ballistics. What happens during the flight of your ammo is studied by External Ballistics. And what happens when your ammo hits the wall, target, falls to the ground, or whatever, is studied by Terminal Ballistics. In this video we are primarily interested in this first part, the Internal Ballistics. Now let us use this slide to extract parameters important for our understanding how slingshots actually work. These are, first, the draw power. You need some power to draw your pouch. And then when you draw, you actually elongate the rubber. So the second parameter, critical parameter, is elongation. These two parameters, they do some work. They have to move, or they have to propel the ammo, the pouch, but also the rubber has to propel itself. So there is some ammo weight, pouch weight, and rubber weight, which are critical for understanding how slingshots actually work. The pouch and the rubber I call the setup. So in this case this is setup weight, and the things on the left I call active parameters, and the things on the right I call them passive. This is not any scientific terminology, but I wanted to make the distinction between, those things on the left which move and do some work onto the things on the right. Now let's talk about critical parameters a little bit more. So we had draw power as first parameter. Then there was elongation, and the third parameter was setup and ammo weight. But there is something very special. Well, we can call it a parameter. It behaves like a parameter, but it's not. It's something which manipulates all these three parameters at once. This is stretch ratio, and it manipulates draw power, elongation, and the rubber part of setup and ammo weight simultaneously. Let me present you the slingshot that I had at my disposal when I made this video, whose parameters I transferred into this program and into this video. I had two bends 2 centimeters wide each, which when I stretch from 15 centimeters, that is 5 times, so for under stretch ratio of 5 to 75 centimeters, I needed 4.67 kilos of power to do that. We shall be shooting a 9.5 millimeter steel ball, which is 3.55 grams, and some others. Pouch weight is arbitrarily 1 gram, and the weight of the rubber itself, that is of these two bends 2 centimeters wide, each 15 centimeters long, is 3.8 grams. And elongation itself is 60 centimeters. We shall now examine our parameters in detail one by one. Our first parameter is draw power, and I want to say that it is very easy to understand and intuitive. If I have these 15 centimeters long bends and I want to stretch them to 75 centimeters, I need 4.67 kilos. And then the question is, what if I want to double the power? You probably know that I have to bring a new pair of bends. But I think that for this analysis it is not enough to say to bring a new pair of bends. What is most important is that actually the first pair of bends were 3.8 grams. So by adding new pair of bends we added new mass of rubber, which is another 3.8 grams, totaling 7.6 grams. I call this draw power to rubber width or draw power to rubber weight relation. Because if we hold cross section of these bends constant, and of course the type of the bends, then there is direct relation or interplay between the width of the bends, the mass of the bends, and the power. As a conclusion, I can say the width of your bends have a direct relation to the draw power. Wider they are, more powerful they are. However, wider they are, heavier they are. This means that if you want to increase draw power by 30%, you must increase the width of your bends by 30%. But the rubber weight will be increased by 30% too. In principle, it is same for tubes, but with some additional consideration, and we shall see how this works some other time. But a more interesting question is how the draw power relates to the velocity and energy. For this I prepared a small table. Here I simulated 12 slingshots, where the first slingshot needs only 1 kilo of draw power, and the last one needs 12 kilos. And from each we are going to shoot 9.5 millimeter steel ball. So as you can see here, as we increase the draw power, velocities in meter per second increase from 34.45 to 86.52 meters per second. Energies also increase from 2.11 to 13.29. And on a graph, this looks like this. As we increase the draw power, the velocity of this 9.5 millimeter steel ball increases. And also the energy increases when we increase the draw power. But there is a catch here. Look at the numbers of velocities. 34, 71, 80, 86 and so on. And look the energies, 2, 7, 10 and so on. So they are not only two different things, velocities and energies, they are on a completely different scale. So in order to be able to compare them in some way, we need to scale them down so that the numbers are comparable. So what I did was to take I took first data of each series and I said they are 100%. And then I work the percentages as they grow downwards in both cases. Now, when I make the graph, now the things look quite different. As we increase the draw power, the velocities increase. As we increase the draw power, energies increase too. But you see they are completely now different. I mean, they exchange their places. And I think that the picture on the right, the graph on the right, is more realistic and more true than the one on the left. So as a conclusion, I can say this. Increasing the draw power for a given ammo weight will increase both velocity and energy. However, the percentage gain in energy will be much higher with each increment than in velocity. In other words, it seems to me that when you increase draw power considerably, you move towards the hunting side of slingshots because that is where energy really counts. Our second parameter is elongation. And what is elongation? Elongation is the difference between your full draw and the length of the active bands. For example, your full draw is 75 centimeters, active bands are 15 centimeters, and the elongation is then 75 minus 15 or 60 centimeters. For further analysis, let me go back just for the moment to the draw power. You remember, 50 centimeters of bands we stretched to 75 centimeters, and these were 3.8 grams of rubber weight. Then, when we wanted to double the power, we actually brought a new pair of bands, that is new 3.8 grams of rubber weight, and then totaling 7.6 grams. But the question is, what if we don't go into the width of the band, but into the length. If we want to double the lengths, all the lengths that we see here. So instead of stretching to 75, we stretch now to 150. Then in order to keep the stretch ratio of 5, we need now 30 centimeters long bands, which when we stretch to 150, we have the elongation of 120. So all these numbers here are the doubles of the numbers here. And it looks like this. This is also 7.6 grams of rubber, just like here. Now let us compare the velocities of these two cases. Actually 3 cases. This is the first case where we have this one pair of rubber, then we doubled this pair, and then this pair we actually doubled in length, not in the width. So this is a normal case, and this is a case A, this is case B. So in the first case, this one, we needed 4.67 kilos, and the calculated velocity of this 9.5 millimeter ammo is 65.26 meters per second. When we double the power from 4.6 to 9.3 kilos, the velocity went to 81.11 meters per second. In order to stretch 30 centimeters of rubber, which is the same width as this one, the same cross section as this one here, to 150 centimeters, we need the same draw power as here. This is important to understand. And then we have new elongation, which is 120 centimeters compared to 60 centimeters. It is doubled. And the calculated velocity of this 9.5 millimeter ball under these conditions is 81.11 meters per second, just the same as here. So, as a conclusion, we can say this: draw power and elongation have an equal influence on velocity and energy. A 30% of increase in draw power is the same as 30% increase in elongation. Or adding another pair of bands and thus doubling your draw power is the same as extending your draw from earlobe to full butterfly or so. For this reason, we do not show elongation to velocity graphs because they are similar to the draw power to velocity graphs that we have seen before. But what is the possible practical meaning of draw power versus elongation? This comes to my mind. If you cannot manage a given level of draw power, but you insist on what this power can offer to you, that is the velocity and energy, then you simply cut your bend, say, 30% narrower or less draw power, but 30% longer, and thus make your full draw length or 30% longer too, of course under the same stretch ratio, in our case 5. In this way you will give up some power for a longer draw and achieve same results. Our third parameter is a group parameter called setup and ammo weight. Out of these, let us first study rubber weight. Why rubber weight itself is so important? We mentioned it a couple of times by now. Simply because the rubber has to propel itself, not only the pouch and the ammo. So if there are two rubber bands of the same draw power, same bandwidth, same stretch ratio and same active band length, then the faster one will be the lighter one. But all the rubber today has very similar chemistry, so that these differences might not be significant. However, rubber weight is significant in itself for understanding how slingshots actually work. Let me illustrate this concept in the following way. I have prepared a small table where I have again my 12 slingshots. The first has a draw power of 1 kilo and the last one 12 kilos. And I have two columns. In the first column, there are the velocities of the 9.5 millimeter steel ball shot from each of these slingshots, but where the rubber weight has not been taken into account, only the weight of the ammo, and the pouch, of course. Here, the second column are the velocities of this same 9.5 millimeter steel ball when the rubber weight has been taken into account. So these are these two cases, without and with rubber weight. On a graph, this looks like this. These are the velocities without rubber weight, and these are the velocities of this ammo with rubber weight. Obviously, there is a difference. Let me bring this concept one step further. We don't have the pouch, we don't have the ammo, we only have the rubber bands. And in our standard set of parameters, our rubber weight of these 15 centimeters long bands was 3.8 grams. But then what if on the market there is suddenly pens on the same characteristics which are only 2.8 grams or 1.8 grams or 0.8 grams and so on? What are the velocities of these bends themselves alone, without pouch and without the ammo? In first case, the velocity is 120 meters per second. In the second case, it is 140 meters per second. In the third case, it is 175 meters per second. And in the last case, 0.8 grams, it is 262 meters per second. It is often said that bends themselves are not faster if they are stronger. Why? For this, we need to go back to our illustration. It's clear to you already. 15 centimeters stretch to 75. This is 3.8 grams of rubber. We need 4.67 kilos for that. When we double this, we double the mass. We came to 7.6 grams and we needed 9.334 kilos of draw power for this. Now, when we divide 4.76 kilos of draw power with 3.8 grams of rubber mass, we get 1.23 kilos of draw power per each gram of rubber mass. When we divide 9.324 kilos of draw power with 7.6 grams of rubber mass, we get again 1.23 kilos of draw power per each gram. So if we ask ourselves what then with velocities of these two cases, then the velocity, the first case and the second case, have to be the same, 120.24 meters per second, because in each case, each gram of rubber weight has the same amount of draw power at its disposal, if I can say so. We can further illustrate this in this way. Let's say that we have the draw power of a slingshot, which is 4.67, then we doubled it by 9, then 14, so that each is doubled. The last one is 28 kilos. And the number of bands in first case is 2, then 4, 6, 8, 10, 12. And the velocities are 120 meters per second in each case, as we have seen before. So on a graph, it will be one straight horizontal line at 120 meters per second, no matter what number of bands or what power do we have in these bands. So, as a conclusion, we can say, no matter how wide, powerful your bands are, the bands themselves, without ammo and pouch, will always have the same velocity. Thinner bands are somewhat faster than thicker bands of equal cross-section area, but it does not mean that the principle does not work. It only means that some other principles might be involved. Now, let us bring ammo and pouch weight in order to get the full picture. Again, I have prepared a small table, where in the first column I have these intentionally exaggerated draw powers, 4.6 to 28 kilos, or 2, 4, 6, 8, 10, 12 bands, and from each we shoot the ammo, which in this case is 5.5 grams. These are the meters per second, the velocities in meters per second. The graph, this looks like this. Now, there's a very interesting question. What if the relation between the velocity and draw power was truly 1-to-1? That is, if we double the draw power, we double the velocity of this ammo. These are these numbers, the theoretical velocity. And on a graph, it would look like this. Of course, this cannot happen. This is non-existent. But it shows probably our intuitive expectations that more draw power, more velocity. Well, it is true, more draw power, more velocity, but not that much. In another case, we shoot ammo, which is only 1 gram, and velocities would look like this. And in the third case, we shoot 10 grams ammo, a heavier one, and the velocities look like this. You see, in each instant, the heavier ammo, lower velocities, lighter ammo has far higher velocities. And Finally, we have the velocity of the rubber alone, which is 120 meters per second. And the whole graph looks now like this. As a conclusion, I can say this. Bends themselves, when there is no pouch and no ammo, are fastest. Lighter ammo and lighter pouch can only approach the velocity of the bends alone but never reach it or become higher. Our second parameter within the group of three parameters, which we called setup and ammo weight, is the ammo weight itself. So let us see how the ammo behaves. Previously, if you remember, we used to hold ammo constant and we had slingshots with various degrees of draw power. Here we shall hold a draw power constant at 4.67 kilos, but our ammo will increase from 1 gram to 10 grams. And as you can see, the velocities of this ammo decrease as the ammo weight increases. And contrary to that, the energy increases as the ammo weight increases. On a graph, this looks like this. As we increase the ammo weight, you see here, the velocity decreases and energy increases. But again, the scales here are not the same. So if we work with percentages, as we used to do before, then the picture looks like this. As we increase the ammo weight, the velocity decreases and energy increases. As conclusions, I can say this. As we increase the ammo weight under the same draw power, ammo velocity decreases. But at the same time, ammo energy increases. In total, the gain in energy here is faster than the loss in velocity. Or, when you increase ammo weight for a given draw power, you will lose some velocity, but your true gain will be in energy. And finally, what about the pouch? The third element from the group of three elements, which we call setup and ammo weight. A pouch is something that we usually, well, I will not say neglect, but we say generally it has to be aerodynamic, it has to be light, and that's it. But let's go deeper into this. For this, I have prepared this table. This column here shows our standard set of parameters, where pouch weight, to remind you, was 1 gram. And if we shoot this 9.5 millimeter steel ball from a slingshot which would have these characteristics, the velocity of this ammo would be 65.26 meters per second. Now the question is, what if the pouch weight is not 1 gram, but let's say 0.5 grams? Then the velocity of this ammo would be 67.9 meters per second, or it will go up by 2.64 meters per second. And finally, what if our pouch weight is not 1 gram, but 1.5 grams, like here? Then this velocity would be 62.87 meters per second, or it would drop down by 2.39 meters per second as compared to the case where the pouch weight is 1 gram. Or, in total, the velocity of the ammo fired from slingshot with 0.5 grams of pouch weight and 1.5 grams of pouch weight is 5.03 meters per second. As a conclusion, what else to say except that our last parameter, and I would say most intriguing one, is stretch ratio. What is stretch ratio? Stretch ratio is the relation between your draw length, or your full draw length, and your active band length. So when you put these into relation, you have 75 divided by 15, which gives you 5. And that's it, the stretch ratio of 5. In order to better understand the stretch ratio concept, let us make a small experiment. I have a rubber band which I stretch 2 times, and for this I need 1.997 kilos. If I stretch it 3 times, I need 3.026 kilos. If I want to stretch it 4 times, I need 4.139 kilos. If I want to stretch it 5 times, I need 4.67 kilos of draw power. And if I want to stretch it 6 times, then I need 6.38 kilos of draw power. This brings us to the concept of stretch ratio function. Here in this table I have the numbers that you have just seen at the previous slide. The stretch ratios are here and the draw powers are here. Let's say that this relates to a slingshot which has two bends 15 centimeters long, which when I stretch 2 times I need this drop and so on. And here you recognize our moment from our standard set of parameters, stretch ratio of 5, I need 4.67 kilos. And this is just for the comparison. This column here shows simply the slingshot which would have not 2 but 4 bends. So how does it look like on a graph? I have stretch ratios here on the horizontal axis, and I have power, draw power here on the vertical axis, and this is the stretch ratio function for 2 bends, in this case. And this is the stretch ratio function for this case of 4 bends, and that's it. Stretch ratio is a very powerful concept, and I would like to show you why and how. You remember, for the stretch ratio 5, I needed 4.67 kilos of draw power. For the stretch ratio 6, I needed 6.38 kilos of draw power. If I put these two numbers in a relation, then stretch ratio of 6 is 36.7% higher than stretch ratio 5 in terms of draw power. Let us use these numbers in the following table. In this first column, I have my standard set of parameters. You remember them, I won't repeat them, except that the steel ball of 9.5 millimeters fired from the slingshot like this would reach 65.26 meters per second. Then the question is, what if I want to bring more power into my slingshot, but not going into stretch ratio 6? Then, as you remember, probably from the section of draw power, that I simply need to widen my bends from 2 centimeters wide each, I need to go to 2.7 centimeters wide each. In this way, I got more draw power, I got 6.38 kilos of draw power, but my rubber weight went up from 3.8 to 5.19 grams. But anyway, my armor reached 72.48 meters per second. And finally, if I decide to go to the stretch ratio of 6, I need to shorten my bends from 15 to 12.5 centimeters, which I stretch to the same full draw of 75 centimeters. Then, 75 divided by 12.5 is 6. So this is a stretch ratio of 6. For this, I need 6.38 kilos of draw power, and my rubber weight is less, is 3.16 compared to 3.8 here. And finally, elongation is higher, from 60 to 62.5 centimeters. And my armor now reaches 79.88 meters per second. Let us now stress the most important points here. In the first case, when I only widened my bends, what was beneficial for this velocity was, I went to 6.38 kilos of draw power in comparison to 4.67. So more draw power. But what was not beneficial for this velocity is for this I needed more rubber weight. From 3.8 I went to 5.19. But in third case, everything was beneficial. The draw power is higher at 6.38 kilos. Elongation is higher, is 62.5, and rubber weight is less, which is also beneficial for the velocity. And no wonder I reached 79.88 meters per second. There are two ways in which we can play with stretch ratio starting from any given setup. Our starting setup is our standard set of parameters, where we stretch 15 centimeters long bends to 75 centimeters. We needed 4.67 kilos for this. Elongation was 60 centimeters. This is stretch ratio 5, and our steel ball then travels 65.26 meters per second. First way in which we can play the stretch ratio is the one that we have just seen in the previous example, or previous slide. And this is when we shorten our bends from 15 to 12.5 centimeters and draw them to the same 75 centimeters of the full draw. And for this we needed now 6.38 kilos of draw power. Elongation is higher, is 62.5 centimeters. Stretch ratio now is 6, and our steel ball now travels 79.88 meters per second. Still, the second way of playing with stretch ratio is keep our 15 centimeters long bends like here, but we stretch them now to 90 centimeters, which is basically stretch ratio 6, because 15 times 6 is 90 centimeters. Elongation now is still higher, is 75 centimeters. We also needed 6.38 kilos for this, just like here. And our steel ball now reaches 85.33 meters per second. This first case is when you shorten your bends, but you draw to your normal draw length, I would say. This second case is when you keep your active band length, but you extend your draw. Some final remarks. When you draw your bends, you actually store energy into them. But while you draw and while you release and so on, you lose some energy into the air in the form of lost heat. You also lose some energy because of the friction between your fork tips and the rubber. So it's no wonder that I calculated this velocity to be 65.26 meters per second on my 9.5 millimeter steel ball, but when I shot it through the chrony, real life, it was 64.5 meters per second, with a difference of 1.16 meters per second. This could be the reason, but also there might be another reason. You remember that there is a critical point where your pouch stops accelerating the ammo. So this calculated velocity is here. And we shoot through the chrony, which is probably 1, 2, 3 or even 5 meters away from this point. So I have prepared a small table here which shows the loss of velocity at first, second, third, fourth and fifth meter. You see, this velocity, the calculated velocity of 65.26 is here at, I would say, 0 meters. At 1 meter from here, 1 meter, it drops to 64.9, then to 64.53, and at 5 meters away from this point, it drops to 63.48 meters per second. So when you see people on YouTube shooting through chronies and reporting whatever velocities are there, 180, 240 feet per second and so on, then you know that this is the velocity at that point where the chrony is, and not the velocity, the exit velocity of this slingshot, which is probably, or not probably, but surely higher. So this ends this video, and I hope you enjoyed. See you in my next video, the flight or external ballistics. Please subscribe, and thank you for watching.